higher in voltage and potential than this right side. We've got a voltage drop. That means that we've got power, P equals IV, and energy is being taken from the circuit and being put into the inductor as a magnetic field. And so we see a voltage drop. It's taking in energy. And this is similar to an inductor, or to a resistor, right? So if you have a resistor here and you have current flowing through it, you see a voltage drop across the resistor. And it's, instead of taking in electrical energy and putting it in a magnetic field, storing it, it's taking in electrical energy and dissipating it as heat. So we see a voltage drop in both cases. So the current's going to the right, and we see a voltage drop in the direction of current. Now, you never see the voltage of a resistor go this way, where you've got the resistor releasing energy, right? Where you have current going this way and a voltage gain across the resistor. You don't see that, but you do see that in the case of an inductor. And when we open the switch and we take away our input voltage and we provide another path for that current to travel in, we actually see the polarity of the voltage switch. And the reason that's happening is because now, instead of taking in energy like a resistor would, it is releasing energy. So it's supplying energy back to the circuit. So we actually see a voltage gain in the direction of current flow, which you'd never see with a resistor. And you can see, like, if you think about it, it's actually what is supplying the power to our output during this time. That's when the switch is open. And you could think of it like a DC power supply. You know, you see with a DC power supply, the polarity is like this, and you've got current going this way. And so as you go through it, you've got negative to positive in the direction of current flow. And here, this inductor has negative to positive in the direction of current flow, and it's kind of acting like our source. So depending on if the inductor is taking in energy or releasing energy, building up its magnetic field when it takes in energy, or decreasing its magnetic field when it's releasing energy back out, it's either going to look kind of like a resistor where it's taking in energy, or an inductor, or a DC power supply where it's giving off that energy that was stored in its magnetic field. So that's why here, when the switch opens, the polarity changes, and this diode is forward biased and current can flow this way. So let's talk about the buck regulator in a steady state. And let's talk about what the inductor current waveform looks like and the capacitor voltage waveform looks like. So we're going to analyze this by first thinking about what this circuit looks like when the switch is closed. So when the switch is closed, this diode is reverse biased, so it just looks like an open circuit, and we have something that looks like this. We'll draw it over here. 4 volts DC. We have an inductor. We have our output capacitor, and we have our V out. Equals 3 volts. So I'm going to break my own rule here. Rarely do I do this, but we're going to figure out the inductor current based on the voltage. So the voltage here is 4 volts on the left and 3 volts on the right. So we see a voltage drop across the inductor, which means that it is gaining energy in its magnetic field, and it means its current is increasing. Remember, E equals 1/2 Li squared. So as the current increases, the energy increases, and we know that it's gaining energy because there's a voltage drop. The left side is greater in voltage than the right side. So now we're going to draw the current in the inductor. This is I, and this is time. So in this example, I'm going to erase this so we can see more clearly. I'm going to assume steady state conditions. And when I say steady state, I mean that Vn is constant and not changing, that V out is constant and we don't want to change it, and that I out is constant and not changing. And here we're going to assume I out equals 1 amp. And we'll talk later about what happens when these things are changing, but for now it'll simplify things if we assume steady state. So the inductor current, for reasons that I will explain in a future video, is going to be centered around I out. It's going to be centered around 1 amp. But according to the equation V equals LDI dt, if we have a voltage across the inductor, which in this case we do, we know that our current is changing. Because the current, that changing magnetic field is what's making this voltage appear. It's a self-induced EMF. And so we know that our slope, our change in current, di over dt, equals V over L. So when the switch is closed, the voltage over the inductor is V in minus V out, and where L is our constant, and so we know that it's going to look something like this. This is our current, and we know our current is increasing because we're gaining energy in our magnetic field, and we've got a voltage drop across the inductor. So here our slope is V in minus V out. In this case it's 1 volt over L. And the switch is closed 75% of the time because we talked about if we want a 4 volts in, 3 volts out, we want to keep a 75% duty cycle and low pass filter, and we'll have an output voltage of 3 volts. So for 75% of the time, our switch is closed. Now, what happens when we open the switch? What does that look like? So now we have disconnected our input from our output, and now we have something that looks like this. This is our V out, still here, our output capacitor. We need a path for that current in the inductor to continue flowing. It still is going to be going this way. But remember now, it's releasing its magnetic energy. It's turning into electrical energy and it's releasing it into the circuit. And so we're seeing a voltage gain across it. And so now this, this way. There we go. Now this diode is forward biased. This negative voltage here is higher than ground. So now we have current flowing here. And what I'm going to do for this example is to assume we have an ideal diode which has a 0 voltage drop across it. So we're going to assume here that the voltage is ground, although it's going to be less than ground in a real life buck. So assume this is ground and assume this is our output 3 volts. So now the didt is V over L, which now is negative 3 volts, negative V out over L. So now here, this slope is V out over L. And we know our current is decreasing because E equals 1/2 Li squared, and our energy is being released from the inductor into the circuit. So now we turn the switch back on and we ramp up our current again, turn it off, ramp it down, and we keep going up and down like this. So the inductor current is going to be centered on our output current, which in this example is 1 amp, and it's going to be going up and down with a slope that we can figure out based on the circuit drawing in the both closed and open switch position. Now, the capacitor is going to playing an important role. The capacitor is always there, and it's always connected to the right side of our inductor, regardless of what the switch is doing in this topology. So here, this is the capacitor voltage, and this is time. So you'll notice that, let's draw the full regulator over here so we can get a good look at it. that we're drawing a constant I out of 1 amp. But the inductor current is going back and forth. Sometimes it's a little bit higher than 1 amp, and sometimes it's a little bit lower than 1 amp. But out of this node, the current's always 1 amp. So this capacitor is actually sometimes providing a little extra current to the output when the inductor current is below 1 amp, and sometimes it's taking in a little extra current from the inductor when the inductor current is above 1 amp. So it's kind of supplying or taking in the current that we need to get the output to be exactly 1 amp. So the inductor, or the capacitor, V equals 1/2, I equals C dV over dt. Getting my equations confused. So if we're going to plot the capacitor voltage, we know that it's going to be centered on V out. So in this example, it's 3 volts. But it's going to be oscillating above and below as it supplies and absorbs that extra current. So here, in this phase here, before the inductor current crosses 1 amp, the inductor current is below 1 amp. So the capacitor has to help supply some of that current to get us up to 1 amp. So in this instance, the capacitor voltage is going down. But as soon as the inductor current crosses this 1 amp, and it starts to get above, it's more than what we need, the capacitor starts absorbing some of that extra current, and as you put current into the capacitor, the voltage starts increasing. So now we're starting to increase voltage. Oh, keep going. And now we get over to here, and now the capacitor is going to have to help out again. It's going to have to supply some of that current. And so we start to drop our voltage until we get back to here, where the capacitor is going to start gaining in voltage again. And my drawing is not good, but basically it's going to be oscillating up and down in a sinusoidal manner as it supplies and then absorbs that extra current. So when you talk about ripple, this is what we're talking about. This inductor current ripple, the capacitor voltage ripple, and as you change parameters like the inductance value or the capacitance value or even the frequency at which you're switching, these parameters change, and we're going to get to that in a later discussion. But that's all we're going to talk about today with regards to this.